Hello, everybody. Let's try something a little different today. An introduction to creating complete 3D scenes using shaders. Yes, I know, this technology called Raymarching has been described many times in other tutorials, and it's hard to come up with something entirely new. Still, I think it wouldn't hurt to add such a video to our collection, because I plan to expand on this topic in a new series, and it would be good to have a reference for the absolute basics. So let's get started. Okay, where to start? I think a bit of theory would be useful because the algorithm we'd like to understand in this tutorial is based on it. Let's take a look at this image. Basically, if we want to display a 3D scene such as this sphere on a 2D screen, we need to perform a 3D to 2D projection. What does it mean? Let's assume we place a camera in front of the screen and trace a ray from the camera lens through each point of our screen. If this ray intersects the scene, in our case the sphere, we know that we should render a pixel in the corresponding color, in our case the yellow color. Otherwise, if the ray doesn't hit anything, like the downward ray in this example, we render nothing. For now, let's ignore the presence of the light source and the shadows. We'll get to that later. So, how do we achieve this in a shader? As we know, the fragment function is called for each pixel, and these calls are executed in parallel thanks to how the GPU works. So, all we need to do is to compute the direction vector from the camera for each pixel, which is a straightforward calculation. The problem arises with determining the length of such ray, and its computation is far from trivial. Basically, there are two main methods. In fact, there are more, but we won't get into that for now. The first one is called ray tracing. This method is often more accurate because it calculates the actual intersection of the ray with objects in the scene, resulting in highly realistic lighting and shadows. However, it is also performance intensive since the intersection calculations can be quite complex. I used ray tracing, for example, in a sky shader where we calculated the intersection of the ray with the planet and the moon. In the case of a simple sphere, the calculation is relatively easy because we were only solving quadratic equations. The second method is called Raymarching, and if we want to render a more complex scene with objects that can repeat, exhibit fractal characteristics, or dynamically merge and separate in real time, Raymarching is usually the preferred choice. Unlike computing an exact intersection, we approximate it by taking incremental steps along the ray, hence the term marching. So, in this image, we can see how the ray begins its journey at the camera lens, which we denote as RO, which is short for ray origin. We then iteratively search for the largest spheres that do not intersect any objects in the scene, denoted as RD for ray direction. After finding such a sphere, we move RO to its center and repeat the process until the sphere collides with a surface where the ray can no longer advance in that direction. Thanks to this method, we need significantly fewer steps compared to advancing RO by fixed increment, making it a fairly efficient way to render a scene. Of course, performance depends on the scene. Some surfaces might make this approach inefficient, requiring further optimizations. But for now, this method works well for us, so let's finally implement it. I will start with the usual scene, so let me right click here, create new scene, and I'll call it Raymarching. Okay, create, and let's add Let's add a color rect because we'll be generating the scene from the scratch. There are no background images. Color rect, and for the layout, let's use the usual dimensions in transform 600 by 400 and scroll down to the material, select a new shader material, click and select a new shader, which is called Raymarching GD shader of canvas item type, and as usual, I'll put it to the shaders folder and create and click again to open it in the shader editor. Okay, so let me start with the usual stuff like deleting the functions we don't need and adding the basic code to recalculate the aspect ratio. Here we go. It would be a uniform parameter, vector2 resolution is vector2 600 by 400, the dimensions of our color rect, and let's use it in the code. What's wrong here? Of course, vector2, no vector3. All right, and here vector2 UV is UV minus 0.5, so we are moving the origin of coordinates to the center of the color rect, and aspect ratio UVX is multiplied by resolution X divided by resolution Y. Okay, so we have the basics of the standard shader with the origin shifted to the center and the aspect ratio adjustment. Now we'll define the vectors RO and RD, which are the ray origin as ray direction respectively, as we know from the previous image. The ray origin is essentially the camera's position from which we'll view the scene, and the ray direction is the direction in which it is looking. So first, let's place the camera at the vertical position of 1 above the 3D origin, so that it hovers slightly above the ground. Let's add the following lines. Vector 3, RO would be, as I said, vector 3 origin, but shifted to the 1 position above the ground. 1, 0, 1. Very well. And the direction. We'll aim it straight ahead. Since we are not concerned with the distance at this point, we'll normalize this direction. So it would be vector 3 RD is, and let's call the function normalize on vector 3. And we need to use the current pixel, so it's UVX, UVY, and 1. The direction straightforward. Okay, so we are ready to implement the Raymarching algorithm. As we can see, as we saw in the image, we'll repeat the steps until we hit a surface. But what if the ray misses all objects? We'll need to ensure we don't run the loop indefinitely. So let's add a uniform parameter called max steps. Uniform int max steps with some hint range, and let's start at 100 steps, and we'll make it from 50 to, for instance, 1000. Why not? Okay. So now comes the most important part of the Raymarching algorithm. How do we determine the value of RD, which represents the current maximum radius of a sphere that hasn't intersected any surface? This is where so-called SDF functions come in, which stands for signed distance fields. Let's take a quick detour to explain what they are and how they work. An SDF returns the shortest distance from a given point in space to a specific surface when provided with the point's coordinates. The sign of the result indicates whether the point is inside or outside the surface, hence the name signed distance field. So let's show it on the simplest example, which is a sphere. The mathematical representation of a sphere in 3D corresponds to this function, where xyz represents the 3D coordinates of the point for which we want to determine its relationship to the sphere's surface, and r is the sphere's radius. Since the square root of the sum of the squares of the components corresponds to the length function of such a vector, we can express this function in the shading language quite simply. Let's add it here and call it sphere SDF. So float sphere SDF with parameters vector 3 for the point. We need to determine its relationship with the sphere, and sphere is defined only by its radius. So let's float r, define the radius. And the function, as I said, would be the length of the point P, and we need to subtract the radius minus r. So we can test this function with various points. Let's assume that the radius of the sphere is 1. So what if, for example, we use the point in the origin of coordinates, so it would be 0, 0, 0. If we use it in this function, we'll get a negative number, namely -1, which indicates that the point lies inside the sphere. If, for instance, we use the point 1, 0, 0, the result would be exactly 0, meaning the point is located directly on the surface. And finally, if we test it with the point 3, 4, 0, we would get a positive value 4. So we can conclude that it is entirely outside the sphere. Okay, so far it doesn't seem too complicated, does it? However, this is just a single object and a very simple one at that, defined only by its radius. In a real scene, we would likely have many more objects of various types, which would make the calculations much more complex, but we'll get to that eventually. Alright, so we can continue with the Raymarching algorithm. As I said, we'll need the SDF function for each object we want to render in the scene. So far, we have only one sphere, so the final code of the SDF function will be quite simple. Let's put it here, float SDF, and for the point vector 3, P. And we need to return all elements we are currently included in the scene. And as I said, there is only the sphere, so let's create this float sphere is the result of the sphere SDF for the point P, and let's put it to some other position than the origin. So we need to subtract the point vector 3. Let's do it, for example, 0, 1.5 to put it above the ground, and 5. Okay, and the radius of the sphere would be 1. And we need to return this sphere. Okay. So the preparation is complete. We can proceed to the actual Raymarching. Let's create the function called Raymarch, which will be responsible for that. Float Raymarch parameters vector 3 array origin and vector 3 array direction. Okay, so let's start with the accumulator, the total distance the array would achieve during this Raymarching algorithm. We'll call it D and return D at the end. Now we need to do it in the cycle. So for int I from 0 to our max steps, so we don't do it indefinitely, and I plus plus and the curly brackets. So we have a loop ready in which we'll implement the extension of our array. First, we'll determine the position of the current end of the array and label this point P. Let's do this. Vector 3 P would be array origin plus D times array direction. We continue by calculating the next step using the SDF function. This gives us the distance, which we add to the current length of the array. So float dist for distance is SDF of the point P, and we need to increase the D by this distance. Okay, This is a critical moment because we need to determine whether the ray has hit something or if we should proceed to the next step. But let's be cautious. We can't simply test the result of the SDF function for 0, which corresponds to a position exactly on the surface, as this could significantly increase the number of iterations under certain circumstances. So, from a performance standpoint, we need to compromise and define a distance from the surface that we'll consider a hit. For this purpose, let's add a new uniform parameter and call it surface dist. Here, uniform float surface dist, hint range, and let's give a small number to the default value, 0.01. And we'll make it from 0.01 to, let's say, 1, and with the step 0.01. Okay, it would be also useful to define a maximum distance so that we don't extend the array indefinitely. We'll add another uniform parameter. Uniform float max dist, again with a hint range, and the initial value would be 100. And we can make the range from 100 to, let's say, 10,000. And the step 0.1 would be okay. And we can complete the rest of the loop in the Raymarch function here. The condition is simple. If the current ray increment is shorter than the surface dist value, so we assume we hit the surface with a certain tolerance, or if the total length exceeds the max dist value, we'll end the calculation and return the current total length of the ray. Let's make it here. So if, as I said, dist is less than the surface dist, which is currently set to 0.01, so it's pretty close, or d is greater than the maximum distance, so we don't want to go indefinitely, and let's assume we didn't hit anything. Let's just break the cycle. Okay, all that's left is to call Raymarch in the fragment function and display a shade of gray based on the resulting value. So let's add these lines. Float dist would be the result of the Raymarch function, and we will use our RO and RD vectors, and we need to display it somehow. So vector 3 color would be simply a shade of gray, so vector 3 with all three components equal to the dist value. Okay, and assignments to the color variable vector 4 with color for the first three components and 1 for alpha. Okay, we still see just white everywhere. Why is that? The RGB components range from 0 black to 1 white, but the distances in our scene are much larger, so everything has blended into white. Let's fix it by multiplying the dist value by a sufficiently small number, which we can add as a uniform parameter and call it something like scale. Let's do it here. Uniform float scale and in range, and initial value 0.5 equals, of course. And let's make it from 0.01 to 1 with the step 0.01. And let's modify the line where we define the color. We will do it like dist times scale, and it's still too big, I guess, so times 0.1. Okay, and we have something here. This is the first result of the Raymarching algorithm. The sphere doesn't look outstanding yet because we are not handling lighting and other aspects, but it's still a sphere. We can try changing the scale value and observe the changes. So, for example, in shader parameters, if I made it lower, we can see how some artifacts are appearing, or bigger. Yeah, it is more in the light shade range. Okay, let's improve our scene a bit. To make it clear that the sphere is hovering above the surface, we'll also display the surface. Its SDF function will be elementary since we'll display it at the height 0, so we'll be only concerned with the p.y value. Let's add this line to the beginning of the SDF function. So here it is. We need to define the ground. Float ground would be simply p.y. Okay, and now if we have more objects in the scene, we want the SDF function to return the smallest distance found. So its current form will look like this. We have the ground, we have the sphere. Let's return the minimum of these two values, min, ground, and sphere. And okay, and we have the result. However, it seems that we once again forgotten that in UV coordinates, the y goes from top to bottom, so the scene is displayed upside down. Let's fix it in the fragment function by adding just this simple line. Where? Here. UV y is simply negative UV y. Okay, this looks nice. Okay, now what? What if we added two more objects so the sphere doesn't feel so lonely? Let's insert new SDF definitions. Right after the sphere definition, we will add a cylinder and a box. Okay, so the cylinder SDF. I think there is a great source of these basic shapes where you can find all these SDF algorithms. So I will just write them here and then add a link to the description of this video. Okay, so vector P, and the cylinder is defined by its height, float h, and the radius of the circle it stands on. Okay, and we return max of absolute value of py, okay, minus 0.5 times h, and length of p dot xz minus r. All right, this is the cylinder and semicolon, of course. And now the box. I'll call it cuboid because we can use it for both the cube and other forms of these cuboids. So float cuboid as the f. And now again, we need vector 3p and all three dimensions of this cuboid: float h, float w, and float d. All right, and the formula would be this one: maximum of absolute value px minus 0.5 times w, maximum of absolute value of py minus 0.5 times h, and 1, 2, 3, yeah, of course, and here absolute value of pz minus 0.5 times d. Okay, we are simply calculating the maximum value of three values. That's why we have some nested maximum functions here. Okay, and let's modify the calculation in the SDF function. We have a ground and sphere. Let's add a cylinder and a cuboid. Okay, so float cylinder is the function cylinder SDF on P And again, let's put it away from the origin. So we'll subtract some other three-dimensional vector, coordinates 5, and the dimensions would be 2 and 0.5. Okay, and now the box float cuboid is cuboid SDF p minus vector 3, and let's put it to the other side of the sphere, so -2 for the x-coordinate, 1 and 5, and the dimensions 1, 1, and for example 0.5. Okay. And again, we need to create a minimum of these 4 values. So it would be minimum of ground, now minimum of sphere and minimum of cylinder and cuboid. Wait for it. Something is missing. Sorry. Ground, sphere, cylinder, cuboid. Cylinder, of course. There we go. You could say we've successfully completed building and displaying a scene with several 3D objects. In the next video, because this one is already too long, we'll address lighting and shadows. Thank you very much for watching. With that, we have completed the basic rendering of a 3D scene using SDF functions. I hope this seemingly simple result hasn't discouraged you and that you'll be motivated to learn the basics of lighting and shadow casting through additional calculations in the next episode. For now, take care and I'll be back again soon.